So now we want to work through a couple examples of static equilibrium problems. And just like a lot of problems in physics, there's really no set technique for solving those static problems. There are a few steps, however, that you can make the process a little bit more manageable. The first thing that you want to do is to stop and make sure that you are, in fact, dealing with a static situation. Look at the problem. Is the net force 0? Is the net torque 0? Is our object not moving? You need to make sure that those static situations are actually static situations. Then you want to identify and sketch out all of those forces. Draw a force diagram. In our study of forces, we drew our system as one little small dot, and sometimes this gets a little bit more complicated when we talk about a static problem, because we're not just talking about one small object. So your force diagrams here might be a little bit bigger, and they might be more of a sketch of, say, a table or a crane or something. I don't know, whatever it is. Even though your net force is 0 and your object is not actually rotating, it could. If one of those forces became unbalanced, then we would have a torque acting on it. So the next thing that you want to do is choose your pivot point. Often this is an obvious hinge or a fixed point, but not always. If there's no point that's jumping out at you that says, hey, this is where it's going to rotate, you can choose any point that you want to, and that's important. It doesn't matter because all of those other forces are going to be in relation to whatever point you choose. You're choosing a reference point is what you're doing. A lot of times it's easier if you choose the point where you have the most unknowns. This is helpful because the point that you choose as the pivot point will create no torque. Choose which direction you want as x, y, and possibly z. Now, the problems that we're doing don't really have a z coordinate. We're only sticking with a single plane, so we're talking about x and y coordinates. However, you have to use that coordinate system to resolve any forces into vectors. Then write your sum equations for torque, the forces in the x and the forces in the y. Be really careful with your signs. Whatever you choose as your coordinate system, up is always up, down is always down, clockwise is always clockwise. Just make sure that you follow the coordinate system that you defined. And then solve for your unknowns. So let's start with a uniform 1,500 kilogram beam, 20 meters long, that supports a 15,000 kilogram printing press 5 meters from the right support. We want to calculate the force on each of the two vertical columns. Now the beam of the table is held up by those two supports, one on the left and one on the right. Any force exerted on the supports will come from the total force of the beam and anything sitting on the beam. In turn, the force that a support exerts on the beam is going to be equal and opposite that of the force the beam exerts on the support. So all of that weight that's sitting on the table is supplying a force downward into the beams. The beams are supplying a force upward to support that weight. The beam on the left we can label F1, and the beam on the right we can label F2. The weight of the beam acts downward at the center of mass, which is located 10 meters from the end. The weight of the printing press acts downward at a point 5 meters from the right edge. Now at this point we don't really have an obvious axis of rotation to write our torque equation, but we can define one. Let's just say that the point where the force 1 is being exerted is our pivot point. So our torque equation will be written from this axis of rotation. This also means that the force 1 will not be a part of our torque calculations because the lever arm for force 1 is 0, which gives us a torque of 0 at that point. This also means that our only unknown is force 2, which is nice because that is what we want to find. Our torque equation then is the sum of all of the torques equal to 0 because there is no rotation. So let's just work from left to right along our beam from our pivot point. We have the torque supplied by the weight of the beam, and that would be negative since it would act in a clockwise direction. The torque applied by the weight of the printing press, also in the negative direction. And finally, the torque that would come from the upward force of the support on the right. This is an upward force, so the resulting torque would be counterclockwise direction, making it a positive torque. We are looking for the force on the second support, so let's rearrange a little bit to solve for that second torque. And we know that torque is force times radius, so we can substitute that in for all of our torques. This lets us solve for the force of the second support and plug in our knowns. Now remember that the force acting on a mass is the mass times 9.8. So the 1,500 kilogram beam has a force of 14,700 newtons acting on it, while the 15,000 kilogram printer has a force of 147,000 newtons. Also note that we are measuring all of our distances from the left support beam. So the center of the mass beam is 10 meters away, and the printing press is 15 meters away. That would make our second support beam 20 meters away from our first support. From here we can find that the force acting down on the second support is 118,000 newtons. Now you might be tempted to say that the force acting on the first support is also 118,000 newtons, but this would be incorrect. We are looking at the sum of all of the forces acting in the vertical direction. So we have to take both of our supports acting in the positive direction and add the forces of the beam and the printer acting in the negative direction. Rearrange for the force of support 1 and plug in all of our forces to find the force acting on the first support to be 44,000 newtons.